When we talk about heat transfer, two important concepts come into play: the heat of fusion and the heat of vaporization. Let's break it down. Firstly, the heat of fusion, denoted as LF, is the amount of heat required to change one unit of mass of a substance from a solid to a liquid state at its melting point. Imagine you can have a kilogram or a pound of a substance at its melting point, and you need to add a certain amount of heat to transform it into a liquid. This amount of heat is precisely what we call the heat of fusion. Secondly, the heat of vaporization, denoted as LV, comes into play when we're dealing with a transition of a substance from liquid to gas at its boiling point. Again, imagine you have a kilogram or a pound of a substance at its boiling point, and you need to add a certain amount of heat to transform it into gas. This amount of heat is precisely what we call the heat of vaporization. The formula to calculate the heat of fusion is given by Q equals m times LF, where m represents the mass in kilograms or pounds, and LF represents the heat of fusion in kilojoules per kilogram, kilocalories per kilogram, or British thermal units per pound. Additionally, the formula to calculate the heat of vaporization is similar. Q equals m times LV, where m represents the mass and LV represents the heat of vaporization in kilojoules per kilogram, kilocalories per kilogram, or British thermal units per pound. Now let's proceed to our first problem. A calorimeter has a mass of 100 grams and a specific heat of 0.900 calorie per grams degrees Celsius and contains 400 grams of water at 40 degrees Celsius. When 91 grams of ice at 0 degrees Celsius is added and completely melted, the temperature of the water is 18.2 degrees Celsius. Calculate the heat of fusion of ice. First, we must identify the givens. The mass of calorimeter is equal to 100 grams. The specific heat of the calorimeter is zero point 0.9 calories per gram degrees Celsius. The mass of water is equal to 400 grams. The specific heat of water is equal to 1 calorie per grams degrees Celsius. Temperature 1 is equal to 40 degrees Celsius. The mass of ice is equal to 91 grams. Temperature of ice is at 0 degrees Celsius. Temperature 2 is at 18.2 degrees Celsius. To calculate the heat of fusion of ice, we first need to recognize that energy is conserved in the system. This means that the heat lost by the calorimeter and water is equal to the heat gained by the ice as it melts. We can express this mathematically using the equation heat loss equals heat gain. The heat lost by the calorimeter and water loss is the sum of the heat lost by the calorimeter and the heat lost by the water, which can be calculated using the formula Q equals mcat, where m is the mass, c is the specific heat, and at is the change in temperature. Similarly, the heat gained by the ice is the product of the mass of the ice, the specific heat of water, and the change in temperature as well as the heat of fusion of ice. Now proceed to substituting the values. 100 times zero point 0.9 times the quantity of 40 minus 18.2 plus 400 times 1 times 40 minus 18.2 equals 91 times 1 times the quantity of 18.2 minus 0 plus 91 times LF. Simplifying this, it would become 10,682 minus 1,656 equals 91 times LF. To isolate LF, we would divide both sides by 91. This would give us the final answer of 99.18 calorie per grams. Now let's dive into the three methods of heat transfer: conduction, convection, and radiation. Firstly, there's conduction. This process involves the transfer of heat within a body through the collision of molecules. Essentially, when there is a temperature difference between adjacent parts of a substance, heat flows from hotter regions to cooler ones. We measure the rate of conduction using the formula Q equals K at over D, where K is the thermal conductivity of the material. A is the cross-sectional area, at is the change in temperature, and D is the thickness. Next up is convection. This method involves the transfer of heat through the movement of liquid or gaseous molecules. Think of how a pot of boiling water heats the surrounding air. Convection occurs as these molecules circulate carrying heat energy within them. Finally, we have radiation. Unlike conduction and convection, radiation doesn't require a medium to transfer heat. Instead, it involves the emission of electromagnetic radiation from a heated surface, which is then absorbed by another surface. This process follows Stefan Boltzmann's law stating that the total radiant heat energy emitted by a surface is proportional to the fourth power of its absolute temperature. The rate of radiation is calculated using the formula presented in our screen, where P is the radiation power, A is the surface area, E is the emissivity, ranging from 0 for perfect reflectors to 1 for black bodies. The Stefan Boltzmann constant, which is approximately 5.67 times 10 raised to negative 8, and T is the absolute temperature. Now let's proceed to the first problem. The thermal conductivity of ice is 5.2 times 10 raised to negative 4. At what rate is heat lost by water in a 6 meter by 10 meter outer swimming pool covered by a layer of 1 centimeter thick if the water is at temperature of 0 degrees Celsius and the surrounding air is at a temperature of negative 10 degrees Celsius? Start by listing down the givens. The thermal conductivity is equal to 5.2 times 10 raised to negative 4. Length is equal to 6 meters. Width is equal to 10 meters. D is equal to 1 cm. Convert it, it would become 0.01 meters. The initial temperature is at 0 degrees Celsius and the final temperature is at negative 10 degrees Celsius. What we're looking for is the rate of conduction. To solve this, we would be using the formula Q over T equals to thermal conductivity times surface area times change in temperature all over D. Substitute the values into the formula, it would become 5.2 times 10 raised to negative 4 times 60 times 0 minus negative 10 all over 0.01. Simplify this, and the final answer would become Q over T is equal to 31.2 calorie per second. Moving on to the second problem, a copper ball 2 centimeter in radius is heated in a furnace to 400 degrees Celsius. If its emissivity is zero point 0.3, at what rate does it radiate energy? Start by listing down the givens. The radius of 2 centimeter. Convert it, it would become 0.02 meters. A temperature of 400 degrees Celsius, it must be Kelvin, so we would add 273, which makes 673 degree Kelvin. Emissivity of zero point 0.3. Stefan Boltzmann of constant of 5.67 times 10 raised to negative 8. Now, what we're looking for is the rate of radiation. But first, we must look for P. We can find the value of P by using the formula of rate of radiation. To isolate P, we would multiply A to both sides. This would give us the formula of P is equal to emissivity times Stefan Boltzmann constant times temperature raised to 4 times surface area. Substitute the values into the formula. 0.3 times 5.67 times 10 raised to negative 8 times 673 raised to 4 times the surface area of sphere, which is 4 pi times r, which is 0.02 squared. Input this into your calculator and it would give an answer of 17.54 watts, and that would be our P. Now, to get the rate of radiation, we need to follow the formula P divided by A. So input the value 17.54 watts divided by surface area of sphere, which is 4 pi times 0.02 squared. This would give us the final answer of radiation is equal to 3489.51 W over m squared.